So today we'll have some tutorial problems. Okay, so the first of all, okay, today we'll have two tutorial problems. Okay, both of them about the double integral, and then second, we'll go back to the lecture notes, and we'll go through the some part of the triple integral, and then after that, we will go to do the third tutorial problem 3. Okay. So then, first of all, then I would like you to take a few minutes to try to do this tutorial problem 1. Okay. So the tutorial problem file can be found on Blackboard. Okay, so I open a new folder for that. So now you might pause the video, okay, for a few minutes. Okay, so you try to work on this problem 1. Okay. So problem 1. So let's start with problem 1A. So in this problem, we are not really going to do the integration, right? We are just going to set up the integration limit properly, right? So again, but let me set up the scenario, right? So we are considering the double integral, right? So that means I have some function, okay, represented by this curved surface, but it doesn't matter what it is. So what we want to do is that suppose I give you this boundary, right? And then I want you to first of all draw the region of the integration, okay, and then write down the integration limit. Okay, so this is the region R. So, and you remember that last time we talked about when we do double integral, right? So there are two possible orders, right? You either integrate along x first and then y, right? Or you integrate along y first and then x. So in each of these cases, you'll find that one is more convenient than the other. Okay, so you just need to determine which one is more convenient, and then you just pick that one. So let's start with 1A. So A is the most simple case, right? So for A, I have 4 straight lines, right? So if I just draw the XY plane, okay. So I have x equals 0 and x equals 10. So this would be x equals 10, right? It would be x equals 0. So these are the left and the right boundary respectively. And then I have the y, right? Y equals 0. And then this y equals 1. Right, so we are looking for the region enclosed by these 4 lines. Then of course is this region here. So then for this one, you understand that it doesn't matter whether you integrate along x first or along y first. It's equally easy. So if I integrate along x first, right? So then I need to go from 0 to 10 EX. And then after I consider one line, right, and then I just basically need to fill the entire region, right, with all these narrow bars. So then my second step is going from 0 to 1. So this is part A, right, so the simplest one. So now let's try to do part B. So this time, what do we have? Again, we have two constant boundary for X. Okay, so that means, let me draw X equals 1 and this X equals 2. So now for the other two curves, so Y equals X squared. So what is Y equal X squared? Y equal X squared will be a parabola, right? And then I have this Y equals X cubed plus 1. So you know that Y equals X cubed is something that looks like this, right? This is a 0, 0 point. And then you need to shift the whole curve up by 1 unit. So that means it looks something like this. So the region bounded by all 4 lines, right, is this. So this time you will realize that it's easier to integrate along Y first, right? Because if you integrate along Y, right, so that means you are cutting the region like this, right? So now let's find the integration limit, right? dy. So this is Y equals X squared. This is Y equals X cubed plus 1. So the lower limit, of course, is for a particular value of X, right, is here. So that means if you are at a particular value, some X value here, then your Y value at this lower limit is X squared. Then I need to consider the upper limit, which is this point. So at a particular value of X, the Y value is X cubed plus 1. So this is the inner integral. So now the outer integral. That would be easy, right? So the leftmost slide is at X equals 1. The rightmost slide is at x equals 2. So that's why I just have 1 to 2. So part C, so let's make some space. Part C. So for part C, I have these 4 lines, right? First of all, the 2 simple one, y equals 0 and y equals pi. This is y equals 0. The y equals pi. So, and the 2 function that I need to consider is x equals sine y and x equals cosine y plus 3. So, well, you know y equals sine x, right? It looks like a wave like this, right? So if I have x equals sine y, then you just basically flip that. So now I have x equals sine y is something like this. So, and then if x equals to cosine y, right, it's just also this curve but shifted up, right, by pi, so with a phase shift of pi over 2. But now I have x equals cosine y plus 3, right? So that means I need to shift the whole cosine curve to the right. So that's why the curve will look something like this. And this is 3. So then again, the region bounded by all 4 lines is this region here. So this time, of course, you'll see that it's easier to cut the region like this, right? So that means you do dx first, and then you do dy. So then again, so this is x equals sine y. This x equals cosine y plus 3. So suppose I am at some value y here, right? So then the lower bound for x is sine y. And this upper limit, upper bound, is cosine y plus 3. So then the dy, right? So the edge is here and here. So then it's from 0 to pi. So the last one, a finite region enclosed by 2 curves. So this time I don't need 4 lines, I just need 2. And you understand why when you plot the graph. So one curve I have is a parabola that opens upward. And the other one is a inverted parabola, right? And but shifted up by 10 units. So you can clearly see that these two curves, right, enclose a region here. So because of these two intersection point, right? So you don't even need two more lines, right, to define the boundary, right? Because I have these two intersection point already to close the area. So so of course you want to find these two intersection point, right? Because that's define the lower limit and the upper limit for the x integral. So all you need to do is to make this 10 minus x squared equals x squared, right? So and then you'll find that you easily find that this is square root of 5. This is minus square root of 5. So now if we want to consider integral, again, you'll see that it's easier to consider the integration over y first, right? So again, for y, right? So I need to consider the y coordinate, this point, the y coordinate of this point, right? So then, of course, this one is given by x squared. Then the upper one given by 10 minus x squared. And then you are going to have all these slides, right? So then, of course, you are going from minus square root of 5 up to square root of 5. So these are all the answers for the tutorial problem 1. Okay. So next, I would like you to try problem 2. And again, let me say this. So these two, if you just look at this integral, okay, you realize that you're not able to find the answer, right, exactly, but you cannot do it analytically, basically. So because if I look at just this part, right, the first integral that I need to take care of, right, you'll see that you cannot do this analytically. And similarly, for this one, you also realize that you cannot get an answer, right, analytically. So then what you consider here is that first of all, I give you these integrals, and I give you all the integration limits. So first of all, you draw the region of the integration. Okay. After that, I want you to try to reverse the order of integration, right? So that means I want to do dy dx instead of dx dy. And then of course these limits has to be changed or re-expressed. After that, look at the integral again, you realize that you can do it analytically. So that makes this question a bit interesting. Okay, so but the skills that you need is actually very similar from the last one, right? So at this point you can pause the video for a few minutes, okay, and then I'll talk about the answer.